Okay, so we're looking at something called asymmetric bending now. So if you remember bending, as you apply a force to something, I guess if you have a beam and you're pushing down on it, you're going to put a moment on it and it's going to cause bending, right? And the upper, like one half is going to be in tension while the other half is in compression. What we've done so far is we dealt with bending where you're applying a force in parallel or perpendicular to the face. So like if you have this piece right here, you're bending it up or straight down. Right now we're going to look at something called asymmetric bending, which is when you're applying that moment in a direction or about an axis that is not one of your traditional axes. So we're going to look at solving this problem here today, where we have a moment that's bending about this axis, that's running at a 30-degree angle down from your z-axis. So you see here, this line right here, that arrow, you're bending about that. And we'll look at how the stress is going to develop there. So we're going to look at a few problems here, or a few pictures, that will help explain what we're looking at. Here's another good picture to look at, kind of viewing what we're doing. You're bending it up about that axis. And so looking at that, you can kind of, intuitively, you know that up here in this corner, you're going to be in compression, while down here you're going to be in tension, right? That's where your maximum tension is going to be, that's where your maximum compression is going to be. So how do we solve something like that? Well, we can break it up. We can break it up into different components. So if you remember from statics, you can actually break up this moment that's bending about this axis into moments that are bending about both the z and the y axes. That way you can take the problem. You solve a problem that looks like this, where you have the moment about this is the moment about the z-axis. The z-axis is shooting right up towards us. I'm going to draw a dot there and call that z. Imagine it's something shooting out right towards you right there. So you have a moment going about that z-axis, and so you can solve for what is, for example, the compression up here, and what is the tension down there. And you can do the same thing about the y-axis, which is shooting right out towards you. And again, you'll have compression up here, and you can have tension up here. And so if you want to find out what's happening in this tension corner, well, if we want to do that, let's solve for the tension from the moment about the z-axis and the tension about the moment about the y-axis, or what's going down on the bottom ledge here and the bottom ledge here, and then add them together, and that'll give us the tension right there in that corner. And that would be our maximum tension in this case. Yeah, all right, well let's go about doing that. The formula that I have written down, or that you can at least reference, is, if you have need of it, is, and I'm actually going to erase most of these pictures so we have more room. Now that we've talked about what we're doing, and just leave this one because that's the one we're going to try and solve for. But the equation that you could write down is your stress is equal to negative moment about z times y over the moment of inertia about the z-axis, plus the moment about the y-axis times the z over the moment of inertia about the y. And so that looks pretty familiar, because remember from just the regular bending, your formula is mc over I, right? This is the same thing. You have the moment of the bending about the z-axis here and the bending about the y-axis here, and you just add them together, just like we talked about before. So let's do that. All right, so let's solve for our moments first. If we have here, we want to know what our our z component is and what our y component is. And so to do that, our moment about the z is equal to, well, that's this component, right? And so that'll be cosine of 30. So it'll be this moment, which we know is 50 pound-inches. So 500 times the cosine of 30. And that is equal to 433 pound-inches. Cool, we can deal with that. I can dig it. And the moment about the y, we'll call it my, is equal to 500 times the sine of 30, which comes out to be equal to 250 inches. Now, if you look at this, our z-axis is positive in this direction and our y in that way. So we actually know that our moment about the y is negative in this case. So we're going to put a negative in front of it. That's going to be a negative moment of 250. Don't forget the signs, because that might screw up your equation or your calculations just a little bit. All right, so let's plug that in. So our stress is equal to our negative m of z. Okay, so that's, we found this to be 433, right? Times our y. Now our y is our distance from that axis, so our y-axis to, well, no, sorry, the distance from the z-axis, so it's from here, the central axis, that distance from there to there, just like when we were doing bending normally. That'll be our y distance. So from the neutral axis, our neutral z-axis to the top or the bottom. In this case, let's look for, what are we looking for? Let's look for the maximum compression. So we're going to look for this spot right there. Let's look for the compression. So we're going to use a positive y. So we're going to times, and what is y? That's half of 3.5, right? That's 1.75. So 1.75 divided by our moment of inertia about the z-axis. Okay, so that's, let's find that real quick. So the z-axis is right here. So it's our bending moment about that axis, right? So it's going to be, for a rectangle, 1 over 12 base times height cubed, right? And this is our base, b, and this is our height. Remember that the base, the b, is always parallel to the axis about which you are bending. In this case, we're looking for the bending moment about the z-axis. We're bending around that, and so our base is going to be b, or the bottom. And when we solve for that, we find that that is going to be equal to, I don't know what I've written down. Let's just plug it in like this then. 1 over 12 base, which is 1.5 times height, which is 3.5 cubed. Yeah, that's that. That's our bending moment for the moment about the z-axis. So now let's do the moment about the y-axis. So we'll do plus, and that's this section, plus the moment about the y, which we found to be negative 250, plus, or not plus, sorry, our z, and we're looking for compression, so we're looking for this distance right here, right? And so that will be 0.75, I think. That's 0.75, yeah, 0.75. And that's in the positive z direction, so it's going to be positive. If we were looking for tension, then we plug in a negative 0.75 right there. But it's positive, so we're going to 0.75. And then the moment of inertia about the y, and that's similar, but now we're doing it about the y-axis, like that. So we're bending that way. So now the base is going to be our 3.5, while our height is 1.5. So we'll do 1 over 12 times 3.5 times 1.5 cubed. All right. So now when we plug that in, when we do the calculations for that, we find that the bending is equal to this section. I found that the bending about the z is going to be negative 23.565 in that compression corner. That makes sense. Negative is in compression. That's exactly what we expected that to be. And the stress about the y-axis, or this section, is going to be equal to negative 31.746 Okay, and I guess we should, well, I'm going to write it like this, 31.746. That way it's less confusing. All right, so the first section was 23.56. That's the bending stress about the z-axis, and the 31.746 is the bending stress about the y-axis. So now when we add that together, we end up with a total bending stress. So we're going to call it sigma bend is equal to 55.3. And that is PSI. And that is negative because it's in compression. And I'm going to move in just a second so you can get a good look at that. And yeah, so basically what we did is we took this picture and we broke it up into its x or its z and its y components so that we could then plug it into this equation up here to find what the bending stress was in this corner, where we knew that the compression would be the most. And yeah, that's a basic overview of what asymmetric bending is and how to look at it.